This is Dr. Hester Jiskoot from the University of Lethbridge with the course Applied Geoscience Rock Roll Quake Shake. This lecture 15 is the only annotated lecture with the remaining topics for this course. This lecture is about these 4 remaining topics that I have not covered yet in the other lectures. The first topic, B-Rock, Building Materials and Geoengineering. In the photo on the left, you see the pyramids of Giza, which are mostly made of limestone, and limestone came from quarries all around the Nile region. So actually a lot of the pyramids were made from limestone because sandstone is more scarce and it's also more brittle. Originally, these pyramids were also covered with a shiny limestone. You can still see a little bit at the top there. In the photo on the right, you see the mosaic floor of the University of Oslo building, the geology building. And these are all building stones that are from all around Oslo, and they include marble, gneiss, granite, schist, and soapstone. The choice of the geological building material depends on a number of factors. Depends on the availability of the material, the cost, the proximity, even though nowadays proximity is not as important as it used to be. What's also important is that the properties of the material fit the purpose. If you choose something as a floor, there's different characteristics that it needs to abide to than if you choose it for a wall or a roof or a countertop or something like that. And ultimately, there's also, over time, there's different fashion and different style that is determining what type of geological material is used for specific purposes. Here you see a list of different types of civil engineering constructions that use different types of stone. So flooring, different types of stone are used then, for example, for roads or for the construction of piers. So all these engineering constructions have specific demands on the type of geological material that they use. To go from a rock or any other geological material to a stone, which is a rock that is used by humans for specific purposes, these geological materials need to have specific properties, and these properties can often be measured by tests. And these properties include the structure, texture, density, appearance, strength, hardness, percentage wear and weathering, porosity and absorption, toughness, resistance to fire, ease in dressing, and the seasoning of the rock. Some commonly used building stones are basalt and trap. Trap is any dark colored igneous, like fine-grained igneous rock. Granite, sandstone and limestone, slate, shale, and marble. Here are some examples of buildings in Lethbridge in which different building stones are used. So the post office, which is downtown, is mostly built of Manitoba limestone, and then the roof of the round roof is made of copper. The Gold Museum, which was actually built as a hospital, so the Gold Hospital, the base, the ground base of that is from sandstone that came from the Monarch quarry, and then the brick was actually made from the Lethbridge Brick and Terracotta Factory. So brick is essentially made of baked clay. And then we have a whole neighborhood, it's called Riverstone, and a lot of the buildings in Riverstone are not built of geological material. They're still wooden houses, but they're often clad like as a decorative layer on the outside by riverstone, which are nicely rounded rocks of different types. Most of the historic buildings in Calgary City Centre are built from sandstone, and Calgary was in fact once known as the Sandstone City. There were quite a few sandstone quarries around. From some of the stratigraphy around the prairies is actually like really full of really good layers of very good quality sandstone. However, most of these historic buildings have been torn down and now replaced by buildings that are mostly built from cement or concrete and steel construction and other types of material. What you see on the right side is a steel construction of the high-level bridge, which is the trestle train bridge in Lethbridge. And as you know, steel is from the geological material iron. Two of the most commonly used modern building materials are concrete and asphalt, and both of these have the main component of these are aggregates, and aggregates are basically crushed rocks of different sizes, so it's sediments and rocks. And then for concrete, the additive is a paste of water and Portland cement, and that sets. However, if you build something that is higher than 10-15 centimeters in depth, you actually need to strengthen it. So you need to add rebar, which is a frame of metal reinforced bars. And if you don't do this, the construction is not strong enough. And you can see here on the right the Hotel Caledon, which was built in the early 1900s, where they had not added this rebar. Which is now just a skeleton left, but it was found unsafe. For asphalt, which is also made of mostly aggregate, about 95% is aggregate, and then we add an asphalt binder, and the asphalt binder also is made of a geological material well known to you. It's petroleum crude oil or bitumen. So when we heat that, it's moldable and you can actually roll it out as we do now. So yeah, both these materials is like mostly geological material. The next remaining lecture topic is UROC, the University of Lethbridge Campus Geoscience. If you've walked around campus, obviously not in this COVID semester, but at other times, you may have seen a lot of other kind of decorative rocks all around campus. Now, a couple of years ago, I had an independent study student, Yongjing Fan, and I had him map all the mostly erratic rocks around campus. So most of these rocks are gneisses or granites or other types of crystalline rocks that originally come from the Canadian Shield and were kind of brought to the southern Alberta region by the ice sheet, so that's why they're erratic rocks. And obviously they were not deposited in the location where you find them now. These are humans that actually moved them around. But anyway, we made a map where there's 2 walking tours of half an hour, and you can visit about 25 rocks and each of these half-hour walking tours that start from the University Student Union. University of Lethbridge Geoscience obviously also includes the local geology of southern Alberta, because all the buildings of the university are built on that local geology. So here we have U-Hall, the main building of the University of Lethbridge, which was designed by Arthur Erickson. And you can actually see the different layers of rock and sediments deposited that the buildings are built on. So that includes the Cretaceous formations, the Dinosaur Formation and the Bear Paw Shale Formation, and then the Saskatchewan gravels, the Tertiary gravels, and then on top of that the glacial tills. And then we have some of the fluvial deposits and some of the sand dune deposits that are of the Holocene. At the University of Lethbridge, we also offer our students courses as well as independent studies that have geological content. So on the top left, you can actually see the collection of geology of the rocks of the Waterton Glacier National Park that was gifted to the University of Lethbridge, that was then made into a project, and now we have this as the University of Lethbridge Library digital collection. So a student was involved in that. On the top right, you see a student measuring one of the concretions at Red Rock Coulee, where several independent study students have done their projects. And then the bottom left, you see a rock slide that fell on a glacier in the Canadian Rockies that is also material for students to study. And then obviously we see a really large erratic, like the Glenbow erratic, where I'm taking some of my courses to do field work or field trips. The next topic in the Applied Geoscience course is T-rock. I taught you how to think like a geologist by teaching you some of the basics and the theories. However, there's also some other elements that I have not touched upon yet. So we've talked about time and space and scale and systems, but I have not talked in detail about some of these systems. So one of the most common and simple depictions of the Earth system is all the way from the Earth core all the way to outer space as like a layering of layers, like layers of onions or ogres, and where you see from the Earth interior all the way to the atmosphere all the way to outer space. But in fact, it's not as simple as this. In previous lectures, I've shown you different models of the Earth interior that depict different types of systems thinking that you can have in terms of studying the interior of the Earth. One is basically the materials, the static composition, which is kind of more like the previous slide, the discrete kind of layering of it. But then you can also have the dynamic composition where we can have either a plume or a plate model, and each of these systems actually emphasizes different types of processes and materials that are involved in these processes. So each model is a type of framework in which we can organize a complex system. And geological sciences include a lot of different topics. So there's time, there's space, and there's the systems thinking. And if you want to like put this all in one framework, you can actually do it either in terms of words that you see on the left, or in terms of like including some pictures and shading or coloring that actually like tie together different types, different elements of this system. Now, this is taken from a fairly recent paper that made an attempt for a simplified geological framework for the Earth and all the environment. So it includes the element of time, and it includes the interaction between the different layers, and it includes all the spheres, the geosphere, the atmosphere, the hydrosphere, and the biosphere. So here you see 4 different models in which we can depict different types of processes and frameworks of the elements and the processes that are occurring in and on the Earth. Dependent on like what you study, some of these models may be better than others to depict this. And as I said in the previous slide, what they attempted to do with the center one is to include everything that is part of the geological framework for both the Earth and the environments. So you see some of these things translate between the different models in which we can depict these different systems. So here you see an example of the same paper, 2018 paper that I showed you earlier, of that geological framework, where we now look at one location on Earth, Iceland, and then we actually look at it over time. So it includes the plate tectonics, it includes the plume volcanism, and then it includes the more quaternary climate change that's going on and the Anthropocene. So ultimately, there's still a lot of kind of unanswered big questions in geosciences, and there's actually no time in this lecture to cover all of these. So why rock actually remains why rock. So here's a couple of these questions where we don't know all the answers yet. And a couple of years ago, I actually had my students each do a project on some of these questions, and you can find the links and you can find them in the lecture notes on online. You can click on the link. So if you want to know more about each of the questions on the following slides, you just have to go to the lecture notes that I actually sent you. So here's a number of projects that I had students do a couple of years ago, either as a wiki presentation or as a YouTube video or as a website. And you can see on this slide and the next slide some of those big kind of remaining questions in geosciences. So I conclude this lecture with just a number of random geology books that I found in my house that I would recommend. The top right is kind of a children's book, Everybody Needs a Rock, and you all know about that because of your rock collection. Then the two in the bottom left are more about the philosophy of geology and environmental science in a way. The bottom right are a little bit about the history of geological exploration. And finally, here you see some course books of 1000, 2000 level geoscience courses, as well as some guide books, some geological guide books of Canada and as well as North America. And actually for almost every state and every region in Canada, we have kind of a roadside geology book. So if you're more interested in that, I would recommend you kind of look up when you can go on a road trip again after COVID. Bring a roadside geology book and use the knowledge that you've gained in this course.